So in this video I'm going to introduce the concept of chain homotopy. Okay, so to explain what this is about, let's go back to the kind of crude informal picture of homology which we discussed right at the beginning of the course. So here we were kind of thinking of chains as subsets of X. And so K chain is like a K-dimensional subspace of X. Okay, so yeah, so suppose we've got two maps, F and G, say, from X to Y, and a homotopy, H from 0, map from 0, 1 cross X to Y, between. So that means H of 0x is equal to F of X, H1x is G of X. And suppose for simplicity that H is ejective. Okay, so this kind of is basically in order to kind of make the pictures we want to draw a bit clearer. Okay, okay. So now let's consider a chain. U in X, and so then. So I kind of thicken it up. Okay, so I mean here's my X, say, and then there's my chain. Let's say it's like a two simplex there. Then I'm going to fatten it up. So there's the top copy there, and we're looking at the like a sort of triangular prism type thing inside. This is kind of 0, 1 cross X, and and then it's kind of got Y is like over here, and we so we apply H to this. So this I'm going to call sigma of U. So that's a subspace of Y. It's kind of so again it's a sort of triangular prism type thing over here. Okay. So the question is kind of what's the boundary look like? Okay, the whole story about homology. We've got these chains sitting in X or in Y, and we look at their boundaries. Okay, so. So we look at the boundary of sigma U. So this is, it consists of the top and the bottom and the sides. Okay, but remember we're supposed to have these various conventions about orientation and signs and so on. So if we take that into account, it's going to be like plus or minus the top, plus or minus the bottom, plus or minus the sides. Okay. And but what are the top and the bottom? Okay, over here the top. Remember this is because of this fact here that H0x is F of X and H1x is G of X. The top, that means that the top is basically the image of U under G, and then this is the bottom. Because the other end of the homotopy is F, so this is just the image of U under F. And then what about the sides? Well, so you take if we take the boundary here, there's kind of U, and then the three edges on the boundary of U, and then and what we do is we sort of take the interval crossed with the boundary to get the kind of sides of this prism over here, and we apply H to it. We get the sides of the prism over there. So the sides is sigma of du. So you've got du is the union of these three edges, you thicken them up, vertically and then map over by h, you get the sides of this prism over here. And so, if we, it's like I say, there's these plus or minus signs which kind of come from the orientation conventions, and if you work those out correctly, what you actually end up with is d sigma u, moving this guy over to the other side, you get plus sigma of du is the top minus the bottom, f g hash u minus f hash u. Okay, so this is kind of what we expect to see coming out of a topological homotopy, and so the definition, the algebraic definition of a chain homotopy is just designed to mimic this kind of informal picture here, and then to connect it up back with the theory of topological homology, we have to do a version of this story here that's kind of that's adapted to our official definitions in terms of chains, in terms of syntheses, instead of chains as just subsets of X. Here's the formal definition. That A star and A prime star be chain complexes, and F and G from A star to A prime star be chain maps. So just recall what that means. That means dF is FD and dG is GD. So a chain homotopy from F to G is a system of maps SK, and these are going to go from AK not to A prime K as in a chain map, but up 1 degree to A prime K plus 1. Okay, that's supposed to reflect the idea over here. If U is K dimensional, then sigma of U, that's more or less just the unit interval crossed with U, that'll be K plus 1 dimensional. So that's what we've got over here. So you've got system maps SK from AK to AK prime 1, such that DS plus SD is equal to G minus F. Okay, so let's just kind of spell out which groups are involved here. So you've got AK and A prime K, and then up here you've got your A prime K plus 1, and down here you've got your AK minus 1 here. Okay, and so you've got your D going there, and your D prime, say, over here, and your G minus F, GK minus FK going across here, and then you've got your SK here and your SK minus 1 here. So what you're really saying is that GK minus FK, and this is D prime K plus 1, say, and that one's DK. So this should be D prime K plus 1 composed with SK plus SK minus 1 composed with DK. Okay, so that's what it looks like if we put in all the indices. Usually we could just, don't need to write the indices, we can just write DS plus SD as G minus F. Okay, okay, so, and then we say F and G are chain homotopic if exists a chain homotopy. Yep. So lots of kind of things are going to be formally very similar to what we did with ordinary homotopy of continuous maps between topological spaces. So in particular, we've got these kind of basic ideas. So 0 is a chain homotopy from F to F, and if S is a chain homotopy from F to G, then minus S is a chain homotopy from G to F, and thirdly, if S is a chain homotopy from F to G, and T is a chain homotopy from G to H, then if you look at S plus T, that's going to be a chain homotopy from F to H. So that's telling us that the relation of being chain homotopic is an equivalence relation. On the set of chain A star, A star, A prime star, that's the set of all possible chain maps from A to A prime, and we've introduced an equivalence relation on that set. And we'll put H chain A star, A prime star is the set of equivalence classes. In other words, it's the quotient set. We take the set and we take the quotient by that equivalence relation that we just discussed. Okay, so that defines these sets H chain AA prime. Now, if you think back to what we did with topological homotopy, a kind of key thing that we did was to show that we had a category H top. The objects were topological spaces and the morphisms were homotopy classes and maps. And we can do the same again here, but we just need a little proposition to justify that. Yeah, so we've got so we've got chain maps like so, and F naught is chain homotopic to F1, and G naught is chain homotopic to G1. Okay, then our claim is going to be that G naught composed with F naught is going to be chain homotopic to G1 composed with F1. And so firstly, this condition here, F naught chain homotopic to F1, means that we can choose these maps S here from SK from AK to BK plus 1 with DS plus SD is going to be F1 minus F0. And then we also choose similarly, because we've got this chain homotopy from G0 to G1, we can choose T from BK to CK plus 1, DT plus TD is G1 minus G0. Then we're going to put U is going to be G1S plus TF0. So in more detail here, you've got your AK here, in your BK and your CK here, and BK plus 1, CK plus 1. Okay, so so we can do our S first if we want, and then our G1, or alternatively we can do our F0 here and then follow it by T. Okay? And so our u is the sum of these two terms. The first term is going this way and then this way, and the second term is going this way and this way. This is not a commutative diagram. You get different things going two ways around anyway. We add those two things up. Then so yeah, we've got du plus ud. So that's dg1s plus dt f0 plus then your ud terms is g1 g1sd plus t f0d. Okay. Now remember that g1 is a chain map. So dg1 is the same as g1d. So it's g1ds, and then this one here I've got a dtf0. I'm going to write that down here. Then I've got my g1sd, and then I've got my last term here, and again here f0 is a chain map, so I can move the f0 past the d, so that's t d f0. Okay, so this is g1 ds plus sd plus dt plus td f0, but sd plus ds, remember that's f1 minus f0, and then dt plus td is g1 minus g0. Okay, and then we just expand all this out. You get g1 f1 minus g1 f0 plus g1 f0, so there's a cancelling, minus g0 f0, so that proves that u is a chain homotopy from g0 f0 to g1 f1. Okay, so we've got composable maps and chain homotopies between them. We can combine them to get a chain homotopy between the composites. So what's the point about that? So it means we have a well-defined composition of chain homotopy classes square bracket G composed with square bracket F is okay, so we've got two chain homotopy classes. We want to compose them. You just choose representing elements of that class and compose those, and it doesn't matter which representatives you choose because of the previous proposition. So this means that now we've got a category of the objects. Objects are chain complexes, and the morphisms are chain homotopy equivalence classes of chain maps. Now I want to claim that the homology functor sort of factors through this. So here's a kind of key proposition. If f and g from a star to a prime star are chain homotopic, then f star and g star are the same. Okay, so we look at nth homology group, say, and you get induced maps. F and G, they both induce a map on the nth, from the nth homology group of A, the nth homology group of A prime, but I want to claim that these induced maps are actually just the same in this case. And so we just obviously have to let so we're assuming that F and G are chain homotopic, so we choose a chain homotopy, call it S. So let's consider some element C in HNA. So C is going to be Z plus BNA, some Z, which is the cycle. So now if we look at, so now F lower star C is the homology class of F of Z. G star C is the homology class of G of Z. So we need to prove that G of Z, square bracket GZ is square bracket FZ, which is the same as saying, just by definition of these homology groups, that G of Z minus F of Z is in the group of BNA prime. In fact, we know that D of S of Z plus S of D of Z is G of Z minus F of Z. And that's kind of what it means to say that this is a chain homotopy. Okay, but S of D of Z is S of naught, right? This is a remember, this Z was a representing cycle, so dz has to be 0 for any of this to make sense. So, so here we've got S of D of Z is S of naught, which is naught. So this second term here we can ignore. So now we've got G of Z minus F of Z is D of S of Z. And so it's D of something, it's in the group BNA prime as required. Okay, so that proves that if you've got chain homotopic chain maps, then they give you the same effect in homology. So as a corollary of that, okay, so we've got means that in order to know the effect of a map in homology, you only need to know its chain homotopy class. So that means we can regard a homology thing as a functor not from chain to AB, but as a functor from H chain to AB. Okay, so that's basically everything we need to say about the purely algebraic theory of chain homotopies. But the key thing we need to do is to connect that to the topological picture. But we'll do that in a separate video.